Lesson 4.8 is on analyzing equivalent expressions. So the question is, how can we write equivalent expressions? How can writing equivalent expressions show how quantities are related? So on page 237, if you look at the solve and discuss it, how many toothpicks make a triangle? 2 triangles. Write an expression that represents the number of toothpicks needed to make X triangles that appear side by side in a single row as shown, and explain your reasoning. So we can start off pretty simply with this. So obviously, if we have one triangle, would be 3 toothpicks. You might think 2 triangles would be 6 toothpicks, but remember what we're doing is we're extending this and we're staying in the same row. So actually, 2 triangles altogether, we need 5 toothpicks. We could continue this for 3 toothpicks. We would need 7 toothpicks. And going one step further, for 4, we would need 9. Okay? So looking at this, you might detect a pattern going on, which is helpful. So observation here would be that number of toothpicks is increasing by 2 each time. Okay, for every increase of 1. Kind of what we're looking at here, this is kind of dealing with like rate of change or slope that we've talked about before. So toothpicks goes up 2 for every 1 triangle. It's kind of like our rate of change is 2 toothpicks per triangle. So if this is, let's say if this is like our X and our Y here, well, it says write an expression, so we're not going to worry about y equals. But since our rate of change is 2, we're going to start out with 2x is going to be a starting point, and then we can see how we need to modify that, or if we need to modify that to get that to work. In other words, if 2x was my expression, if I put a 1 in place of the x, 2 times 1 would be equal to 2. Okay? But I actually, for 1 triangle, I had 3 toothpicks, not 2. So if I got 2 and I wanted to get 3, I just have to modify that slightly. To get from 2 to 3, we would have to add 1. We add 1, then that works. Check it out for the next one. You try it with 2 triangles. So, whoops. 2 times 2 is 4, plus 1 is 5. And you can continue that, and that will work for anything. Okay? So this would actually be our expression. All right? And again, what it starts out is just an observation. We're increasing by 2 toothpicks for every 1 triangle, and then we can just modify that if we need to. What number do we need to add or subtract in order to get that expression to work? Example 1, a new box of pasta claims it contains 25% more than the usual box. What expression shows the amount of pasta P in the new box? Okay, so there's our boxes. And so if P is the original amount of pasta, they didn't really do a great job of defining that, maybe, but if P was the original amount of pasta, we have 25% more. Well, 25% of what? 25% of what we had originally, okay? So 25%, you know 25% as a decimal is 0.25, okay? So to find 25% of P, we would take 0.25 times P, and then we're just going to add that to the p that we had to begin with. In order to add those are like terms. And you might say, well, yeah, they're like terms, but I don't have a number. Well, just remember, if you don't have a number, 1 to the rescue. We can always put a 1 in front of something. Multiplied by 1 doesn't change it. And then, so essentially we got 1p plus 0.25p. They didn't really need to put the parentheses there that they did. That's fine. Doesn't hurt anything. Anyway, you add those together, you get 1.25p. And if you think about it, it kind of makes sense, because to start with, we had 100% and we added on 25%. We have 125% of p. And that would actually be a different way of doing the problem and getting the same answer if you want to go that route. So on the Try It, Joe is buying gift cards that are on sale for 15% off. He uses C minus 1500C to determine the sale price of the gift cards. What is an equivalent expression Joe could also use to determine the sale price of a gift card? Okay, so this one is going the opposite. Instead of adding a percent, we're subtracting a percent. So C minus 1500C. Once again, in front of the C, we could put a 1 there. And then these are like terms, so we're allowed to combine these together. So essentially, we're just going to take 1 minus 1500ths. When you do this, make sure you line up your decimal points when you go to subtract those. So when you subtract, if you're doing this by hand, technically we'd be borrowing across here. And then we would get 85 hundredths. So this would be 85 hundredths C would be our expression. So using this bar diagram the book's using, to fill in these, we could say this is 85 hundredths C, and then this is the 1500ths C that we're saving. And then you can see those two combined together would make 1C or just C. Another approach you could do to this problem would be that you could say, well, full price would be 100%. We're saving 15%. So when you subtract, that's 85%. So 85% of C, and that'd be 0.85 C as well. Okay? Either approach that you want to use there is fine. Example 2, some middle school students will use 1-foot tiles to create a frame around a large square mural painting with side lengths S feet. 3 students each wrote an expression to determine the number of tiles needed. Are these expressions equivalent, and explain? Okay, so the first one said, if S is like our rectangle part there, we've got S plus 1 across the top here, S plus 1. Over here we've got another S plus 1. And then this would be another S plus 1, and then this would be another S plus 1. So they're saying we need 4 S plus 1 sections, so we could do 4 times the quantity S plus 1. That works. The second person is saying we've got an S, we've got a 1. 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 And so they're saying we've got the 4 S's, S plus S plus S plus S, and then the 1s, they just added those together, plus 4. So that works. Okay? Then the last person, they said all across the top here, it's a S plus a 1 plus a 1. That's S plus 2. And then they said this is S, and then here's another S plus 2, and then here's another S. So we have 2 S's, and we have 2 S plus 2's. So that works also. And the question is, how is it that all 3 of these people can be correct? Well, if we think about it, these all would simplify to the same thing. In other words, this first expression, if I distribute That'd be 4 times s plus 4 times 1, which would be 4s plus 4. So 4s plus 4. The second one, we could put 1s in front of our s's and we could combine those together. And that would be 4s plus 4. And then the last one we could distribute into the second part here. So 2 times s plus 2 times 2. So 2 times s is 2s. 2 times 2 is 4. And then 2s plus 2s is 4s plus 4. Okay, so if you'll notice, all three of those we were able to simplify down to 4s plus 4. Example 3, a table with a rectangular top has been extended with a table leaf as shown. Multiply 3 5/10 times the quantity 6 5/10 plus x to write an equivalent expression for the total area of the extended table. What does each term of the equivalent expression tell you about the table? Okay, so we know the area of a rectangle is length times width. So that's why the book is saying we're going to do the 3 5/10 times 6 5/10 plus x. The 3 5/10 actually is our width technically, and then the other one is our length. But when we're multiplying, excuse me, when we're multiplying, we can change the order of these, and we'll get the same thing. So just like the book said, we can do it this way. Instead of putting the 6.5 plus x before the 3.5, it'd be the same thing if we multiply it this way. So anyway, you multiply that out, you can see what the book did, multiplied, and then they got 22.75 plus 3.5x. And then what happens, it works out to where the 22.75, that was 3.5 times 6.5. Well, if we look at this picture, that actually would be the area of the original tabletop. And then the leaf got added. Leaves, I guess, can go anyway. Most of the ways that I've seen leaves actually get added in towards the middle of the table. But anyway, they're just trying to simplify things for us, I think, here, putting it on the end. And then the 3.5x would just be the area just of the leaf part of the table. So if we look at the try it, we've got a similar idea. Total area in square feet of a rectangular stage has been widened by x feet is represented by 1,900 plus 76x. Use the distributive property to factor the expression. And what does the factor in the equivalent expression tell you about the stage? What does each factor tell you about the stage? Okay, so this one's kind of backwards from what we did on example 3. Okay, so they're asking us to factor this expression. So what we're going to try to do is we're going to try to look at these numbers and see what they have in common. And again, this would be something with calculators. We could potentially check this quicker. We could try taking 1,900 divided by 76 and see if that works out. And then if that doesn't work, we can work our way down from there. And it actually works out. If you take 1,900 divided by 76, you'll get 25. So what that means, if you remember, factoring, we're going to take a 76 out in front, and we're going to think about what would we have left, so that when we distribute, we would get 1,900 plus 76x. So we said 76 times 25 was 1,900, and then we would need 76 times what to get 76x? Just x or 1x if you want. Okay, good. So this would be our factored form for this problem. So if we look at our picture, then we can try to look at what these mean for us. So let's just move this over here by our work so we can kind of see a little bit better maybe what's happening. And what you might notice, one of our factors is 76 and the other one is 25 plus x. Well, we already have an x the one way, so we might guess that this would be a 25 there, because then that would make this whole thing x plus 25 or 25 plus x. And then our other factor is 76. And if you think about that, that makes sense then, because we're doing the area of this whole thing. 76 is the length, and then x plus 25 is the width. So we had in other words, we had a 25 by 76 stage to begin with, and then we increased the width by x. We kept the length the same. We kept the length at 76. It's page 240. We're going to look at number 2. Total area in square feet of rectangular mural that has been extended by x feet is represented by 5 5/10 times the quantity 7 5/10 plus x. Expand the expression using the distributive property. What do each of the terms in the equivalent expression tell you about the mural? Okay, so we're going to take their expression first of all, and we're going to expand that. And I'm not really expanding it there, I'm just making it bigger. So when we distribute these, we do 5 5/10 times 7 5/10 plus 5 5/10 times x. And when you multiply the decimals there is 41 25/100. And then plus 5.5x. So we basically, this would be our expanded part. And then kind of like the example we looked at earlier, one of these is going to be our original area of our original rectangle. The other one's going to be the area of our new rectangle. So the number part is going to be our original. That's the ones that we knew. So 41.25 square feet would be the area of the original mural, and then 5.5x would be the area of the extension. So if we go over to number 5, a rope is used to make a fence in the shape of an equilateral triangle around a newly planted tree. The length of the rope is represented by the expression 9x plus 15. Rewrite the expression to represent the 3 side lengths of the rope fence. So if we factor out a 3, out of this 9x plus 15, whatever's left in our parentheses, since it's an equilateral triangle, that would tell us what each side length of our triangle would be. So 3 times what to get 9x, that would be 3x. 3 times what to get 15, and that would be 5. So this would be a rewritten expression. And then the length of one side, well, we had 3 times something, gave us the perimeter basically, or the total length of the rope. So the length of one side would be 3x plus 5. So we're going to look at some problems here. Workbook page 59, starting with number 2. Area of a rectangular outdoor stage has been extended on one side. Entire new area is 216 plus 12x. Factor the expression to find the dimensions of the extended stage. And understand when they're saying find the dimensions, that means the length and the width. since it's a rectangular stage. So we're going to look at this. We're going to look at the 216 and the 12 and try to figure out the biggest number that those can both be divided by. So both those are actually divisible by 12, so that means 12 is the number we can factor out. So 216 divided by 12 is 18. In other words, 12 times 18 is 216. And then 12 times 1x is 12x. So this would be our factored form. And then they want us to find the dimensions. So what we can do is think about the number part must have been our original, which was 216. What we need to think about is that both of these had a 12 in common. The 12 is in common means 12 is the dimension that stayed the same even when we made our extension. And then the 18 is going to be our other part, and then the x is the part there that got added on. So in other words, 12 is one of our dimensions, and 18 plus x is our other dimension. Okay. But again, I wanted to draw the picture out so you guys could understand and not just say, well, one of the factors is the length, the other one's the width. Hopefully that kind of helps you to see how we know what is what. So if we look at number 4, the manager of a store increases the price of a popular product by 5%. Let T be the original price of the product. The new price is T plus 5/100ths T. Find an expression equivalent to T plus 5/100ths T. So there's different ways we could get equivalent expressions. Ideally would be by combining like terms. In front of that T we can put a 1, and then if we add those together that would be 1 and 5/100ths T. Okay, and if you're not sure on doing that, you can work it out this way if you're adding those by hand. Okay, then part B, if the original price was $24, what is the new price? So the original price, it tells us in the problem, is T. So what we could do, one option would be just to substitute 24 into our new expression, and you get 25.2, which means $25.20 if you add a 0 on the end there. Another way, which actually is kind of a nice way if you want to double check yourself and know that you did it correctly, is what you guys would have done before. Maybe you would say, well, we need 5% of that to figure out what is being added on. And you get that would be 1.2, which is $1.20, and then you take 24 plus $1.20, and you get 25.20. Okay, so that's a nice way of double checking it. That's another way that you could work the problem out as well. And understand basically what we're saying here. You know, it was 100%. We're increasing it by 5%. Means we're paying 105% of the original price, and just 105% changing to a decimal is 1.05. So that's another way of thinking about that. Number 5, a landowner recently sold a large plot of land. The sale decreased his total acreage by 12%. Let V be the original acreage. Write 2 equivalent expressions that represent the new acreage. So the word decrease means that we're going to be subtracting. So we started out with V, and then it decreased by 12%. So the 12%, that's 12% of the original acreage. So 12% as a decimal times whatever the original acreage was. That's what we're subtracting out. So that would be one equivalent expression. And then we could put a 1 in front of this. We could actually subtract. We could combine these together. Another way of putting this would be 88 hundredths V, which basically says if we decrease by 12%, we still have 88% of what we started with.